And so the general chemistry introduce the enthalpy first, and which is equivalent to the energy. The absolute enthalpy, it is still unknown because we don't know all the energy forms in any matter. So the actual change is more relevant. The delta H, that's enthalpy change. This enthalpy change is the heat exchange or energy exchange at constant pressure, which is normal reaction condition under constant pressure. The enthalpy change, it is the sum of enthalpy formation among the product minus the sum of enthalpy formation for the reactant. And the enthalpy formation, it is defined as energy difference between the reactant, depends the chemical, the substance, and from those the elements, pure elements. Pure elements and they're most stable from delta HF is 0. So anyway, delta H is just the difference between the reactant and product. Use of product minus reactant. We can also estimate the enthalpy change for the reaction. Use the bound energy. And the bound energy equation, it is just it is opposite. It's all the bound energy in the reactant minus all the bound energy in the product. So that's in the chemistry first semester. We use a bound energy to estimate reaction enthalpy change. And then the exothermic reaction, endothermic reaction is because delta H, the change is positive or negative. The change is negative means final product has less energy than the reactant. The energy difference, it is released. So that's heat being released, exothermic reaction. And why does this equation look familiar? Okay, the same equation here. I'm going to move forward. Move on. The same equation. The bond dissociation energy is energy to break the bond. And the breaking bond, there are two ways. One is the pair of electrons between two atoms equally split. Equal split. And those single arrow means one electron movement. Okay, single, the fishhook arrows. And when you have the fishhook arrows, this is a situation, one pair of electrons, the electrons, pair of electrons split. One go with one atom, the other go with the other atom. And that's the homolytic, means equally split between the two atoms. This bond dissociation produces the atom or a group of atoms with unpaired electrons, with one unpaired electrons. And these we call them radicals because electrons unpaired. So there's another way to break the bond is a heterolytic. Heterolytics is the bond dissociate. This pair electron goes with one of these two atoms. And that way the end is whichever atom have no electrons to go with becomes cation and the other becomes anion. That's a heterolytic bond dissociation. And so the bond dissociation energy we discussed to estimate the reaction enthalpy change, it comes from the homolytic bond cleavage, or bond dissociation. And so these are the energies for a different kind of bond. There's no point we need to memorize this. We won't need to memorize this. Just kind of need to have a rough idea. Some bond is very strong. You can see they compare the bond energy with large numbers means very strong bond. So for example, the hydrogen fluorine bond is a very strong bond. And the weaker bond, you can see the hydrogen iodide bond is very weak. By the way, this has a lot to do with the acidity. Okay, with the halogens, hydrogen bond with a halogen can dissociate, becomes acid. But the acidity, hydrogen fluorine, hydrofluoric acid is very low pK, very high pK, weak acid, which is whereas the hydrogen iodide is a very strong acid. You can see the bond energy explained, even though the bond dissociation is different. The HI bond is much lower bond dissociation energy, so which means easy to dissociate, which make the hydrogen, make the acid a strong acid, and so forth. You can see some other, the strong bond, by the way, strong bond oftentimes means they are more difficult to react. So there's some bond is very strong. So for example, hydrogen bond, hydrogen carbon bond is very high number. So these bonds are very hard to dissociate. That make them explain why the alkane is very stable, because alkanes have those kind of bonds. Alkane also have the carbon-carbon single bond, which is also very high. So, and you can see the halogens, just pure element halogens, fluorine bond is very low energy, which explains why the fluorine gas is highly reactive, because this bond is easy to dissociate and react with some other chemicals. Yeah, so that's the exothermic or endothermic. There's something we can predict. So these are the little quick practice. It depends on what kind of reactions, and also depends on the bond energy we can predict qualitatively. Is endothermic or exothermic? So first one, hydrogen atom, hydrogen with one dot, that's hydrogen atom with a fluorine atom. Each one have unpaired electrons with one dot. And this is the kind of situation, they are highly unstable. Hydrogen and fluorine both at room temperature exist as diatomic molecule. So when you see those, the hydrogen atom and fluorine atom, these are unstable. So once they become together, their reaction is these two electrons will join together, a share between the two. So this is once you form bond, is much more stable. The product is more stable than the reactant, so that's typical exothermic reaction. And the next one, the CBr bond is broken. The bond broken almost always endothermic, because bond is when the two atoms share electrons. It is more stable than the two atoms separated, which is just reverse, just opposite to what you see the first question. So bond broken, if you write down the equation, let's say if you write down the equation, this carbon will have 1 electrons, and bromine take the other 1 electron, and that's the become unstable. These two, the carbon with unpaired electrons or bromine with unpaired electrons, are the high energy species. So you need energy to reach that high energy level, endothermic. Okay, number 3, the strong bond is broken, a weak bond is formed. So strong bond is broken. When you break the strong bond, you need more energy. Okay, when the strong bond is broken, need high energy. Weak bond is formed. The bond is weak, as we can see from the last slide. Weak bond need less energy to break. The reverse is true. When the weak bond is formed, it release low energy. Okay. When the strong bond is formed, it release high energy. When the strong bond is broken, it require high energy. For the weak bond, it'll be low in both. To break the weak bond, you need less energy. And when the weak bond is formed, it also release low energy. It'll be just like the first two questions. These first two, one is bond forms, this is bond forming. And the other one bond broken. Bond broken need energy, endothermic. So anyway, when you have this kind of reaction, to break the strong bond and form a weak bond. So you can see qualitatively, okay, qualitatively, the energy needed is higher than the energy released. So the combined effect is you will need more energy. You will need more energy, which means it is endothermic, qualitatively speaking. Okay, because this process, it needs more energy, even though it releases a little bit of energy. Combined together, it is endothermic. The other way to understand this, when the strong bond is broken, let's say you will need just kind of a semi-quantitative. You need 200 kilojoule energy. Whereas the energy, this is how much energy you need to add to the reactant, okay, to break the bond. Weak bond is formed, it will produce energy, release energy. Let's say the bond is weak, so release a little bit of energy. The combined effect is plus 200 added with negative 100. They combine, it is still positive, which means the reactant overall still need energy to make this happen. So use the bond energy relatively, we can predict this reaction, endothermic or exothermic. And so the question number 4 is completely opposite. Weak bond is broken, so you need because the bond is weak, so need a low energy to break. Don't need a lot of energy to break. When the strong bond is formed, it release high energy. So what is the combined effect? Need low energy but produce more high energy. So combined effect, it is in the end, it still produce energy, which will release energy. So the overall effect is exothermic. So when you consider the this kind of question, so keep in mind the qualitative. It's kind of like a relationship. The relationship, if it's a bad example, let's say you break up your old friend and make new friend. So is your new relationship worth it? When you have to break up your old friend and make a new friend? It depends. If you break up a very strong bonding old friend, and form a very low level of new friend, that's net is loss. It's kind of like this. And with the energies, you consider the net effect. There's new bonds formed and old bond broken, and the effect is which one is stronger. Depends on which one is stronger. And so that's the answer key for those. The potential energy diagram, this we have seen in general chemistry many, many times. The first one, the exothermic, because the final product lower than the reactant. And this delta H is negative because the delta H is energy of the product minus energy of the reactant. And this is the activation energy. Okay. This is activation energy for the forward reaction. This is the activation energy for the reverse reaction. From the reverse, from product become the reactant. That's reverse activation energy. And endothermic reaction is just the opposite. Okay, endothermic is a cooler reaction. The final product have a lower temperature than the reactant. That's typical for endothermic reaction. And entropy change, it is entropy is described the degrees of molecular freedom or disorder, randomness. That's the entropy. Entropy is a measure of disorder, freedom, or randomness. And the entropy, as we learned in the thermodynamics second semester, there's a second law of thermodynamics. We can use that to predict if a reaction is spontaneous. If the change of entropy for the universe. If the universe entropy increases, and that change will be spontaneous. And the universe okay, there's two bar about the Zoom. It's kind of getting my way. I cannot see my stuff. Okay. The total entropy change, or the universe change of entropy for the universe, it is have a system and the surroundings. And that's in the thermodynamics second semester, general chemistry. We introduced that. For the reaction to be spontaneous, this total entropy change must be positive. And that's the if the total entropy change is positive, means the forward reaction is spontaneous. If the total entropy change is negative, means reverse will be spontaneous. We learned in the second semester general chemistry, eventually this spontaneous or not spontaneous, it is actually means the reaction equilibrium constant larger than 1 or less than 1. Okay, what really in the end means, actually the spontaneous means it is equilibrium constant, larger than 1 or less than 1. Larger than 1 means products favored, and less than 1 means reactant favored. And so that's the chemical reactions. We see the delta S total. It comes from the system entropy change and surrounding entropy change. And in the chemical reaction, especially organic chemical reactions, the reaction always takes place in a solvent. And so the entropy change of a system, which is a reaction, the surroundings for organic chemical reaction, it is solvent. It is solvent that is surrounding those solute where the reaction takes place. But this surrounding entropy change oftentimes very difficult to assess. The system entropy change, many times we can easily predict. So we still focus on the system entropy change. And so these are some situations very common in the organic chemistry, the entropy change, it's a system between the reactant and the product. Entropy change can be easily determined by how does the reaction takes place. So for example, the decomposition reaction start from one reactant becomes 2 or more product. This kind of dissociation, once bond dissociate, the component A and B have more freedom. Is a typical entropy increase. And so that's the reaction producing more molecules, especially the reaction. If the product has more gas molecules than the reactant, the entropy is increasing. This is, by the way, still the system entropy change. Keep in mind, in organic chemistry, we rarely discuss about the solvent entropy change. It's more complicated to describe and predict. We mainly focus on system. Okay, even the molecule did not decompose, but within the structure, some bond broken. And so, for example, when you have a ring structure, after reaction, part of the ring bond breaks, becomes an open structure, or called acyclic, have no rings. This is also have more freedom, because A and Y, X and Y in the beginning has to be tied together. But after reaction, X and Y, because there's so many free rotation we can have, X and Y have much more freedom after the bond between these two dissociate, breaks, has more freedom, and therefore the entropy also increase. Both kind of reaction entropy increase. And so we can take a look at some of the reactions. These are, we need to predict what happened to the entropy change. And these are actual organic chemical reactions. The first one is cyclobutane, and it becomes a alkene. You can see there's part of a double bond, alkene. There's a bond breaks. There's some other changes. There's some other associated changes. Actually, not only this bond seems like break, there's also the hydrogen atom shifted. But in the end, what really matters, okay, the hydrogen, you can see one of this hydrogen reattached to join here. But the hydrogen bonding, shifting, and change does not affect the entropy much, because the hydrogen dissociate, breaks from this carbon, but it forms in a different carbon. It forms a carbon. So the net change is pretty much negligible. But significant change is when the ring opens. This is the typical ring opening reaction. Entropy change is positive. And for the second reaction, you can see the two reactant becomes one product. There's the net change in the molecules. And also, if you look at the states, both react in the gas state, and the product is also gas state. The net change in the gas molecule, in the product, there's only one gas molecule. The reactant, there are two gas molecules. So the net change in the gas molecule is -1. You get a decrease in the number of gas molecules. And then when you have a reaction that is you lose gas, you have less gas in the product. That's always, almost always, the system entropy change, it is a negative. The reason because the gas has much higher molar entropy. Per 1 mole gas has much higher entropy than the liquid or solid. So if any reaction, you can see the change in the gas molecules, there's a very definitive prediction about the change in entropy. And this is the reaction. This reaction is also the real reaction. Towards the end of our class, we might see this reaction. It is the ring forms. And this reaction, if you use arrow pushing, it looks very nice. 3 arrows. And those are the double bond shifted. And in the end, between these two carbons, it forms a bond. And so once you form a bond, these two will no longer have as much freedom as before. So there's a loss of freedom. It's entropy decrease. This is also entropy decrease. Knowing the entropy change it helps understand why some chemical reactions require high temperature, and whereas the other reaction prefer low temperature. Because the entropy increase, it is favorable for the reaction to take place. And the high temperature will be helpful for those entropy increase processes. That's why for the first reaction is high temperature preferred, because entropy change is positive. System entropy change is positive. This prefer high temperature. And the others, the B and C, both entropy decrease. High temperature not favorable for the reaction. These two both require low temperature to take place. It will be more favorable for forming product. Okay, surrounding entropy change. This is in the thermodynamics, the second semester general chemistry, we'll learn about this. The surrounding entropy change can be predicted by the reaction enthalpy change. Reaction enthalpy change, we just covered in the beginning of this lecture. And negative, because the reaction exothermic, then the surrounding gains the entropy, gain the energy, and increase in the entropy. Okay. the surrounding entropy change to have positive, because second law of thermodynamics prefer, if any entropy change, if the positive change is always favorable for the reaction that takes place. And so the entropy change have two parts, system and surroundings. The system, not so much you can do for a chemical reaction. For a given reaction, entropy change is fixed for the system entropy change, like we did previously, so slides. And the other part, it is the surrounding entropy change. It depends on the reaction, exo or endothermic. The exothermic reaction give heat to the surroundings, makes surrounding entropy increase. And because that's why the exothermic reaction favors the product, because the exothermic reaction give heat to the surroundings and tend to have the positive surrounding entropy change. Anyway, combined together, we have the Gibbs free energy. This is the equation we've seen in the second semester. You have an entropy change minus temperature, the absolute temperature, and the system entropy change. These are all system. And this is the, we did a discussion in the second semester general chemistry. This Gibbs free energy decrease, which means the reactant has more Gibbs free energy than the product, then this reaction will favor the product. Okay, when the product has less free energy, the product will more favored, or the K is larger than 1. That's what the product means. Product is favors for. So how does that make it happen? Because this equation has two pieces. You have an entropy part, and you have the enthalpy part, and there's the entropy part. So these two need to work together to make the reaction move forward, to have the product be more preferred. So how to make that happen? This is part completely based on the second semester general chemistry. And I just quickly go over that because we discussed it quite extensively in the second semester general chemistry. When the reaction exothermic, that means when the delta H is negative and the system entropy is positive, that will make this whole piece negative. When you have this reaction always spontaneous. It does not matter what temperature. Okay, so that's exothermic reaction, entropy increase. And the reverse, if both are opposite, when you have an endothermic reaction and entropy of system decrease, that reaction never be spontaneous. The reaction never spontaneous, that means the reaction will not proceed, become product without any external interference. For this kind of reaction, even though forward is never spontaneous, if you will be given a external work, it can still take place. But just by yourself, this reaction can never be spontaneous. And these last two is when you have a enthalpy factor and entropy factor opposite, then the temperature make a difference. Okay. Endothermic reaction and the system entropy increase. System entropy increase, this is in favor of the reaction. Endothermic reaction is not good for the it's unfavorable for the reaction to be spontaneous. So to make the reaction become spontaneous, we need to magnify, we need to increase the entropy factor by give high temperature. And so that's the endothermic entropy increase. The opposite will require the low temperature. So when the reaction exothermic entropy decrease, then we need a low temperature. The low temperature because exothermic reaction is in favor of the reaction, in favor. The product has less energy than the reactant. That's always natural. But the entropy is against. The entropy part is the vote against the reaction. Then we need the low temperature. Low temperature reduce the resistance of the entropy factor to fight against the reaction. Make that less effective. And that way you make the energy, the enthalpy factor dominate. So that is how I covered in the general chemistry second semester. Those of you who feels like not quite familiar with this, you can take a look at your notes when you take the general chemistry second semester in the free energy chapter. We had a fairly comprehensive discussion about this. You can even prove that mathematically. Okay, so what about next? Okay, so how this energy is a series. Okay, what really matters in organic chemistry is it depends on what kind of reaction. This is a real chemical reaction. And if you show the arrow pushing, it's kind of fun too. This is you have arrow go this way to form bond, and this bond move away, and this bond move in between. The arrow pushing in organic chemistry is kind of fun to do. Anyway, by doing those arrows, you form a ring. So what about this reaction? How the temperature influences this reaction? So we need to look at both the enthalpy change and the entropy factor. Okay, so this is the reaction start from two reactants become one product. As a matter of fact, this is actually gas. This is small molecules of gas. So there's a net decrease in the gas, and there's less freedom in the product. The entropy system is decreasing, is negative, because there are more linkages being formed. What about the energy? This reaction, we start from these two. The alkenes are the high energy molecules, and the final ring is a low energy molecule. This reaction is exothermic. So how exactly exothermic? Well, you can use bound energy to look into that. But for our class, we don't need to predict which molecule have high energy or less energy. In general, organic molecules, more double bond, more triple bond means higher energy, and more single bond, especially carbon-carbon single bond, those are typically low energy. So that's why if you look at the reactant molecules, there are 3 double bond total. And in the product, there's only 1 double bond. So the product have a low energy than the reactant. Anyway, product have low energy than the reactant. That's exothermic reaction. This is exothermic. And you can see the reactions is enthalpy is exothermic. This is a vote for, this is in favor of the product, in favor of the product. But you look at the entropy is decreased, so this is not in favor of product. To form a ring, entropy atoms, molecules, less freedom than the beginning. This is against. How to make this reaction move toward the product? It is since the entropy is against, to make the entropy less effective, we can lower temperature. Because the lower temperature, it'll make this part less less influence. This part is vote for yes, and this part is vote for no. We need to weaken the resistance. Doing that, we can just use low temperature. And so that's how actually the energy, enthalpy, free energy, and free energy and entropy work together to promote certain reactions. We apply the 2 parts, consider 2 parts, entropy and enthalpy, these 2 parts. And we have some new term. This is the exergonic. Exergonic means when a reaction or any change, the graphs, the y-axis, instead of energy, we use free energy as a Y. The energy diagram we learned in the general chemistry second or first semester, those are the either enthalpy, mainly the enthalpy change. In the organic chemistry, we more use the free energy as Y. And the X is still the reaction coordinate or reaction progress. The left hand are the reactant. That's the same as the potential energy diagram. These are the reactant. And the product on the right hand side. So when you have a reaction like this we call the exergonic. This is the related to the exothermic. But keep in mind, they are not the same because free energy has the entropy factor. Free energy has both enthalpy and entropy. Exothermic, it is only the enthalpy change. Exergonic is free energy change. So when you have the exergonic reaction, means the product have less free energy than reactant, and therefore the delta G is negative. Okay, delta G is negative change. And when we have delta G is negative means the product is favored, or the reaction favor the shift right. The product is favored. In other words, use the equilibrium constant. It means the K equilibrium constant larger than 1, which means at the equilibrium there will be more product than the reactant. Okay, so if you plug in the K larger than 1, in the end your delta G will be negative. So that's exergonic. Endergonic, basically just opposite. The product have a more free energy than the reactant. This is not spontaneous, or it means this reaction, as a reversible reaction, the reactant is favored. And also the K equilibrium constant will be less than 1, which is the same thing. Same thing as the reactant is favored. The delta G and the equilibrium. For exergonic reaction, the reaction eventually will reach equilibrium. And the lower, compared to the reactant, the free energy of the product, the lower it is, means there will be more product formed, or you have a higher equilibrium constant. The delta G is more negative, that means the equilibrium constant be larger. But in organic chemistry, we rarely actually use the relative magnitude to compare. Which one has more product than the reactant? We rarely use those. Equilibrium constant or equilibria constant, it is the product of a reactant. That's typical we learned in the organic chemistry. And this is how the K is expressed. Use the equilibrium concentration. And the K also relates to the free energy change. The equilibrium, as we learned in the general chemistry second semester, equilibrium, it means the reaction dynamic. At any moment, always the reactant become product. At the same time, meanwhile, the product molecules reverse, become the reactant. Most organic chemical reactions are equilibrium, reversible reaction at equilibrium. And so that's equilibrium is when the forward and reverse reaction rate equals. When these two reactions reverse forward equals. And so the next topic is also review on the organic chemical reaction. Is the reaction kinetics. The kinetics, it means the reaction rate. The reaction rate is different from the reaction equilibrium. It's related, but different. The reaction rate depends on the concentration of reactants. For most reactions, when the concentration increases, reactant increases, the rate always increases. The second one is activation energy. The activation energy is just opposite. Activated energy means the energy barrier for the reactant molecules to become product. So when you have high activation energy barrier, make it difficult for the reaction. That means the reaction will slow down. And then number 3, temperature. The temperature, it gives the increase the average kinetic energy for the molecules. And so the higher temperature make more molecules be able to overcome the barrier, overcome the activation energy barrier to react. So high temperature is enabling. It is promoting, allow reaction to proceed faster. High temperature means rate will increase. And these two, the both 2 and 3, we have an equation we call Arrhenius equation in the general chemistry to describe. Number 4 is geometry and sterics. This is in the organic chemistry becomes oftentimes very, very important. So we'll see numerous examples in the future reaction. Keep in mind, we did not really discuss the geometry sterics in the inorganic reactions. But organic chemical reactions, there'll be more part of the molecule. They can get in the way of the reaction, and that can influence the reaction. Last one, catalyst, that reduce the activation energy by providing an alternative reaction pathway. The rate law. The rate law is the first part in the second semester general chemistry. The rate law in organic chemistry is not super critical, but we need to kind of know. That'll help you understand some reactions, why some reagent concentration matters, whereas the others not so much. It is because the reaction rate depends on the concentration of reactant, but may not to the same degree. And the degree of the concentration influence rate, it is, you can see by the order. Orders, it is basically exponent on the concentration, the power on the concentration. And the orders found out from the experiment. The rate will be the rate constant, and the concentration raised to power. Those power are the order. And so that's the rate law in general chemistry second semester. We have some discussion in the second semester. Let's say we have, this is a reaction. A and B are the reactant, and C and D is product. And this is a situation, what do we find out? The reaction is the first order for reactant A, first order. And for the reactant B, zero order. Zero order means the power equals 0. So that way, the any variable, if the power is 0, it means equals 1. This number divided by itself, so always equals 1. So what is the difference the order makes? And that's when you change the concentration, you can see the difference. Because A and B are the reactant. So if I change the concentration A and B, there may be some effect on the reaction rate. Okay, with this reaction, what do you find the A is the first order and B is 0 order. Then the rate law, it becomes only the reaction rate only depends on the concentration of A and is independent of a concentration B. So therefore, if the concentration A is doubled, when the concentration double, K being the constant, your rate will double. The reaction rate will double if the concentration of A is doubled. Okay, what about B? Okay, B is also the reactant. Well, supposedly we increase B, the reaction rate should increase. But you look at this rate law, this rate have nothing to do with B. So that means the B concentration may be double. The reaction rate will remain constant. Remain constant or remain unchanged. So that's what the order means. The order means, let's say we want to speed up some reaction. We need to know the rate law, because we will only change the concentration of the reactant that is in the rate law, not keep changing with the concentration for the reactant that is not in the rate law. For here, the B is not in the rate law. This rate law don't see the B. So changing B, concentration B have no effect on the reaction rate. Okay, so this is a different reaction. This is more common in organic chemical reactions. We have a reaction A and B, and the rate law shows us is the first order for both A and B. So that means if A doubled, the rate will double. And also B, if B doubled, keep A the same, when change B to twice as much, the rate also will double. This is the situation, since both reactant show up in the rate law, the concentration change of both reactant will influence the reaction rate. Activation energy, we explained this is the activation energy from the reactant become product. The high activation energy means a lower reaction rate. So that's the difference when you have a two reaction energy profile. One is have the smaller activation energy, will be faster. And the right hand is higher barriers and have slower reaction. So the analogy will be the high jump. When the people are high jump, or the hurdle race, run the hurdles. The hurdle is higher, then it slows down, make it difficult for the acid to pass, to clear. Temperature increases the reaction rate because it shifts the population of the reactant molecules more to the right-hand side, make more molecules be able to qualify for the reaction. So this is the typical distribution of gas molecules with respect to the energy. The low temperature, the average energy is in lower position, average. High temperature, by average, you move to a higher energy status. And what's more important is the area that is above the energy threshold, the activation energy. Increased temperature, the red area is much bigger than low temperature, which is the blue area. So that's basically explaining why the high temperature reaction faster. So if you use a hurdle race, some of you watch the hurdle, hurdle in the fusion track. You notice the athlete is almost run as fast as they can to clear the hurdle. If someone did not run and try to clear a 1 meter high hurdle, that's very difficult, very high chance of bump and fail. So just like the molecules, when the molecules have more energy, there will be more molecules qualified for the reaction to clear the hurdle, clear the barrier, become product. Okay, geometry effect. This is a very unique, almost only in organic chemical reactions. So in our past, we learned about the isopropyl methyl, isopropyl, tert-butyl, and we've seen the tert-butyl really preferred on the equatorial position, much preferred in the equatorial, in the cyclohexane as a substituent, which is much higher than isopropyl, and also much higher than methyl or ethyl. The reason because when you have a tert-butyl, those hydrogens really sticking out. make it hard to more bulky. So what's the effect on the reaction rate? All of these, this is the actual reaction. Okay, so what the difference? The reactions, it is a hydroxide, the lone pair attack on the carbon. And same time, this bond will break, carbon-bromine bond will break. These three reactions are very similar. But what do we find out as chemists? We studied the relative reaction rate. The acyl bromide is fairly easy to take place. Because acyl bromide, there are two hydrogens, small hydrogen atoms, make it fairly easy to access, to attack for the hydroxide. Well, when you have replace one of the two hydrogens with a methyl group, this is kind of getting in the way, block more spaces, make it a little more difficult for the hydroxide to attack on the carbon and then kick away the bromine bond. So the reaction rate, this is actually slower because there's a big chunky methyl group kind of getting in the way of attack. Reaction is slower. When you have more bulky groups in the organic structure, it makes the reaction slow down. That's very common. You see this kind of situation all the time in organic chemical reactions. Just because the methyl group has one carbon, three hydrogens, and those three hydrogens sticking out. This is kind of hard to see, but if you this is when you have two hydrogen. And when you have a two methyl group, the situation becomes more crowded. You can see the access to this carbon from this direction is just more blocked. This situation becomes much worse when this carbon attached with the three methyl groups. Three methyl groups in the three-dimensional, you can see this completely blocked the access. The attacking hydroxide have no access to the carbon to react with. This is much, much worse. Not allow the reaction to take place. So just kind of show you this is how the geometry affects the chemical reaction. The catalyst, it goes through a provided alternative reaction mechanism and reduce the activation energy and make the reaction much faster. So what about this is a summary on the reaction rate, how it's been affected by all these factors. The first one, concentration, and then the temperature and activation energy, that's a very big factor. Steric effect, in organic chemistry becomes very common, very, very common. After the midterm exam, we'll get into some reactions. We'll see the steric effect affect the reaction pathways. And so the reaction energy diagram. The same energy diagram now have two things to look at because we have two factors. One is the reaction rate, and the other one is the reaction equilibrium, thermodynamics. The activation energy, as we can see, the low activation energy allows the reaction to become faster. That's only one part, because low activation energy oftentimes make both reactions, both forward reaction and reverse reaction faster. So in the end, will the product be favored or not? It still depends on the equilibrium, and which is the free energy change. The energy barrier for the reaction, that affects the reaction kinetics. Okay, how fast the reaction. How low it is for the product compared with the reactant. This affects how the equilibrium constant K. So now we have two things to consider in the chemical reaction. What is the reaction rate and also the final equilibrium. So there's the terms in the chemistry we just need to know, but I will not get into too much into our exams. The first one is a kinetically favored pathway, which means faster reaction. Okay, what is faster reaction? Kinetic favored reaction is faster reaction is a reaction that has a lower activation energy. Okay, lower activation energy is kinetic favored. And so the you can see the red reaction. This is the reaction between A and B, same reactant. There can be two reaction pathways. One reaction pathway is give you C and D as product. This is a reaction pathway one. Between these two reactions are the competing reactions. Forming product C and D versus the forming product E and F. These are the competing reactions. They both start from A and B. But anyway, the A and B reaction has much lower activation energy. Whereas the reaction to form C and D, this is the actual C and D reaction activation energy. You can see the red reaction is just a lower activation, faster reaction. And so that's the, so when you have one reaction kinetic favored the reaction because a faster reaction at the low temperature is more important. Low temperature kinetic favored reaction give you main product. Low temperature kinetic favored reaction give you the main product. Because all the reactions slower. Since low temperature slow down all the reactions, then whichever faster should give you the more product. So that's the first one, kinetic favored reaction. And the other one, it is thermodynamic favored. If we take a look at delta G, which one has a more negative delta G will be more favored reaction. Same two reaction pathway from the last slide. You can see the from EF is lower activation energy, faster reactions. But from AB become product C and D, the free energy change is much lower. This is the free energy change to form product C and D. And this is the free energy change for forming product E and F. So C and D, because it's a more stable product than E and F, we call this CD reaction as a thermodynamic favored. Because when you have the delta G is lower, your K is larger. This reaction K is larger than the reaction form E and F. Larger K means more favored, the product more favored. So that's what we call it the thermodynamic favored. Okay, so what's the difference between these two? At high temperatures, when the reaction higher temperature, where all the reaction become faster, it doesn't matter the AB becomes CD or it become EF, or the reverse reaction. Okay, we need to consider reverse reaction. At high temperature, all reaction faster. And now since all reaction faster, they can easily reach equilibrium, easier to reach equilibrium. And then since all of them can reach equilibrium, and C and D have a larger equilibrium constant, more favored than E and F, thermodynamic favored reaction is preferred at a high temperature. Okay, thermodynamic favored pathway is preferred at high temperature. High temperature, this pathway is preferred. So the first half of chapter 6, we cover all these bases. energy, bound dissociation, entropy, free energy, enthalpy, and so forth. Eventually, what matters to the organic chemistry is that we should know how the entropy affects the reaction, and also we have a thermodynamic versus a kinetic favors the reaction. We should know which one's preferred at high or low temperature. Okay, so if we go back to the last slide, low temperature kinetic favors reactions is winning, because low temperature all reactions slow. Then the faster reaction will get to product a little faster, quicker. But at high temperature, all the reaction becomes so fast, it can easily reach equilibrium. Then whichever the equilibrium state more preferred will give the main product. Thermodynamic favored, which means the delta G is more negative. This kind of reaction is preferred at high temperature. So this is conversation, discussions, qualitative, and so keep in mind organic chemistry, we have many qualitative comparisons. So get used to, get familiar with this kind of thinking. So this is there's more examples. We have this kind of CND-EF reaction. Okay. This reaction is interesting. We have a red reaction and the blue reaction. And the difference is the red reaction have higher activation energy. So this is slower. This will be a slower reaction. Okay, red reaction now becomes slower. And also the delta G for the reaction is also smaller. So that means this reaction, it'll be slow, and also equilibrium is not very favorable of the product. Whereas if you look at the blue reaction, you have a faster reaction because lower activation energy. And also equilibrium energy is lower. So at the equilibrium CNDs, you have higher concentration. So for these two reactions, the CND reaction is both faster and higher, is more preferred at equilibrium. So this reaction, the CND is always winning. CND is both the kinetic favored and the thermodynamic favored. It takes both. And the reaction produced in the ENF is slower and also gets less product in the equilibrium. So it's losing on both ends. In organic chemistry, this would be kind of nice picture. We don't need to do anything. One of the reaction become dominant. So we're going to the last part, transition state. I will stop here. Okay. In the future, in our midterm, we don't cover the transition state.